Okay. From Beijing, from China, and good evening to Dr. Fini also in the US. Very welcome to 111 Intelligent-Based Program and Young Lecture Room Series, sponsored and initiated by the School of Civil Engineering. And introduce global expert talents in different fields of civil engineering to present their latest research findings and their research work to faculty members and students so that they become familiar with the current state of the art in different fields of civil engineering. So thanks for their support. Yeah. And actually, we in the key laboratory of highway engineering of Sichuan province, we decided to provide 3 lecture series on sustainability and resilience of transportation, infrastructure, materials, as one of the topical subjects that in recent years attracted the attention of many scientists and scholars worldwide. And so, paradigm for production, modeling or characterization of novel materials, bio-novel materials, so that which leads to sustainable development, environment protection, and finally having a circular economy. Yeah. For today's presentation, the title is about use of end-of-life plastics in bituminous composites, and the presenter and our speaker is to accept our invitation. Associate professor and at Arizona State University, and also she's serving as an invention ambassador at the American Association for the Advancement of Science, a Fulbright scholar of Aalborg University of Denmark, and a senior sustainability scientist at the Global Institute of Sustainability and Innovation, and director of the Innovation Network for Materials, Methods, and Management. And her research focuses on production, characterization, and atomistic modeling of sustainable novel materials for use in construction. She has published over 200 papers and invited as a speaker for many different events and platforms. And also her research has been featured by BBC Women in STEM, Science Nation, Wired Magazine, CNBC. And also she's currently editor of the ASC Journal of Materials in Civil Engineering, and the top journal of resources, conservation, and recycling. And also she has served as the president of ASC North Carolina Northern Branch and the program director of the National Science Foundation. And also in recognition of her achievements, her dedication to during her research career, she won many awards, including an NSF Career Award, ASCE Gerald Seeley Award, BR Amorth STEM Innovation Award, and many other awards. So it's really it's an honor that we have Dr. Fini here, and she accepted our invitation. Thank you so much, Dr. Fini. And before I pass on to Dr. Fini, I just want to ask everybody that during the presentation, please, if you have any question, don't hesitate to type and send your question to me in the chat box below in at the bottom of your window, the Tencent meeting window. You can tap on the chat and please send it to me directly, your questions, and at the end of the presentation, yeah, I will collect all the questions and will read them, and Dr. Fini will respond to everyone. So I hope everyone especially students, actively participate during this presentation and also our next presentation, so that it will be arouse their scientific curiosity and make up their ideas for their future research. With that, yeah, now I will ask, I will share, I will stop sharing my yeah, and we'll pass it on to Dr. Fini. Yeah. Okay. Yeah. Yeah. Thank you, Dr. Fini. Yeah. Welcome.
Thank you, Ali, for the introduction. Hello, everyone. Good morning, good noon, good afternoon, wherever you are in any part of the world. I want to talk to you about, as Ali mentioned, waste plastics and what we call waste plastic and why do we even care about them. So I'm going to start with this art, sort of cover art. Is actually painted by my sister, Elva, who actually was inspired when he saw all the problems with the plastics in America and everywhere in the world, really. During this lecture, I'm going to ask a few questions, and I want you to think about it and maybe write your answer in chat box. So this is not a typical seminars when you listen and, you know, sort of forget about it after a few weeks. I want you to reflect and think about what are the challenges in today's pavement and transportation as in general, and as a student, if you are listening, what can be your contribution to address those challenges, whether it's in China or in America or anywhere else in the world. You can make a major impact by realizing and recognizing true big challenges. So if you think about this art, is actually showing how this whale is running away, and it's sort of ironic because the whales don't have anywhere to go. So imagine if he's running away from ocean, in a way it means he's gonna die because there is no other place for him except oceans. And all those little plastics you see there, they are actually representing the plastics that we human dumping into the ocean. By 2025, it's estimated that the amount of plastic in the oceans will be equal to the weight of fish. And by 2050, we have more plastic than fish. So just think about these huge problems. We may just talk about it and forget, but this is not something trivial. It's impacting all of us because you can see fish is actually part of our food chain. So it's not about just whale running away or dying. It's about us being impacted by all those plastic. So that being said, of course, Ali already introduced me. I want to hear from every one of you. If you have ideas or research that you think we can help you, do anything about this problem. So I put my email over there. You can contact me with any questions or things that you want us to help make this challenge go away. When you look at the road underneath my picture, it's actually the road we're going to talk about today. But think about future road. If you can figure out a way to turn the waste into added value product for roads, that could change the future. Right now, this black road is made out of bitumen, asphalt, right? Everybody familiar with that? A sticky, gooey glue that comes from petroleum. Can we somehow be independent of petroleum and come up with renewable sources that are low carbon, that don't pollute the environment, and all the good things? So think about your road and the future road that you will build, because you are sort of in the beginning of your career. As you build your journey, you can build a future road. This three-part lecture is going to talk about sustainability and resilience. We're going to have 3 talks, of course, and Ali will inform you about future talks, but I just want sort of put it here so you have sort of a heads up and you can start thinking and reading about topics that we're going to discuss in these 3 lectures, and come prepared with your question so we can have very informed and engaged discussion. So talking about end-of-life plastics, the word is plastics, right? So many of you think of plastics as one entity, but just like human, like my name is Ellie and Ali's name is Ali. We are different. Plastics are also different. So when you hear plastic, don't generalize them, because every one of them have different characteristics. And I'm going to show you how we deal with them as end of life or waste plastic, and is it even possible to use them in pavement? Here we talk about hybrid coating and some technologies to make plastic like asphalt and go and stay in asphalt. So I'll tell you about technical side. But to start, think about all the waste plastic that goes to landfill. Right now, we are only recycling 12%, and 40% goes to landfill. As you guys already know, China is not accepting plastic from America, and you guys are producing a lot of plastic on your own as well. So you end up with a lot of plastic on your side, and we are ending up with a lot of plastic on our side we have to deal with. There is a big need to find alternative solution, because everybody's talking about this problem and the ocean and the fish dying and the whale dying. But think about it from material side as well. These are valuable material. They are made of molecules. These are just called waste because they are in a wrong place, wrong time. But when you look at it from material perspective, these are just molecules like any other thing. I mean, when you throw out your bottle of water or milk jug after it's finished, become a waste. But these are literally polymers and molecules that have been a lot of energy and effort went through to make them. I'm showing you a table of plastic to tell you they are different. You can look at this family of plastics with their name here listed, starting with polyethylene. We have high density polyethylene. It keeps going, PVC, LDPE, PP, PS, and many, many, many others. Each one of them have a different difficulty or ease of recycling. So not even every one of them is recyclable. And then you think about, okay, I want to recover these molecules. I don't want to dump it in the landfill. Well, some of them are easier to recycle, so not too much energy goes to recover the monomer. And you can see the monomer here in the second column. Some of them are nearly impossible, or too much energy is needed to recover them. So we in asphalt and construction overall, in civil engineering, in dealing with aggregate and putting things together, we can think of possibly using some of this material to improve our application. And I caution every one of you in pavement and transportation, think about how we can improve our roads. Obviously, roads are not the cemetery or burial for waste. We don't want to just dump it into roads because we want to get rid of it. If it has value and if it adds value to pavement, then yes. If it doesn't, we don't want it. We are first and foremost, we are engineers, we are pavement engineers. We want to make the road last longer, be more sustainable, and work better. So when you look at this material here, for instance, we did use polyethylene and HDPE, which I will show you in a minute. But when I tell you all about this, molecules and material, one big problem with using them in asphalt is these are two different people. Asphalt has its own characteristic. Each of these plastics have their own characteristic. How do we even know they like each other? So if the bitumen or asphalt is gonna meet PET, are they gonna shake hands or are they gonna push each other away? Is it going to like HDPE or PVC or any other one of this, or is it gonna just kick them out? By saying kick them out or push them away, I mean compatibility. So when you think about plastic and use of it in asphalt, you have to think about, are they compatible? What is the problem if they don't like each other? They're gonna separate. Over time, they're gonna separate and you're gonna have material or pavement which is prone to crack because now you are getting phase separation. So I'm gonna show you how we can actually make asphalt and some of this plastic like each other. And this is one method we have done it. I'm sure many other people are working on other methods, but one step is obviously to try to recover monomer, but that's too much energy and it's difficult in terms of carbon footprint and associated energy consumption. So we decided instead of recovering the monomer, we're gonna grind the plastic and then cover its face so the bitumen thinks it's his friend and is compatible. So here is the covering portion, it's coating. Basically, we are facing plastic face. We are coating, we are covering the face. You can see these granules, the colorful, they are different plastic. We grind them to this fine powder here, and then we use the oil to coat the surface. You may think why we are coating it with waste vegetable oil. In this case, in waste vegetable oil and many other bio oils, we have molecules that can graft or attach to the surface of plastic. So now you have a plastic that it doesn't call itself plastic. So then asphalt may like it because it doesn't see that much of incompatibility. So we call this one oil-treated plastic granules, and that's how it's made. It's a patent pending technology here at Arizona State University, and we're trying to use it in trial roads and section here. So thinking about the method, here you can see different picture of it. The first one was not compatible. We grinded it, and section B here, it shows the non-treated. This one was not compatible. It was phase separating and didn't like asphalt. What we did, we basically treated and changed the surface of this material with biomolecules. And now section C is treated. Even though they look nearly the same, this one is C is very hydrophilic, B is very hydrophobic. And then in the third step, we actually carbon coated it. So this one, hybrid treated granules in section D, is actually carbon coated. So you know that most of bitumen, a significant portion of it is actually carbon based. When we made it carbon coated, it became very compatible, but C was compatible as well. B was not compatible. So as simple as changing the characteristics on the surface, now they can interact better. So I'm going to tell you about the tools, but before going to the tools, because some of you are students, I assume, I think when you face a challenge or you want to start dealing with a big problem, solve a problem, don't worry about the tools. You need to first figure out your hypothesis, research hypothesis, and figure out the problem, true problem, which is, in another word, we call it research gap. So if you found out the research gap and come up with a good hypothesis on the solution side, then the tools come in. You can find the tools to do it. But right now, for us, the problem was compatibility, and the hypothesis was by changing this face of granules, we can make bitumen to like plastic. So now the two, they like each other. So our hypothesis was, can we change the surface of the granules? That was the question. And then we need tools, right? So we need tools to see if we really change the granule surface. If you just look at them, B and C, they literally look the same. Yes, D may be different color, but B and C are the same. Yet one is compatible, one is not. So now the tools come, but do not mix. And I have many students that think they have to start with the tools and run a bunch of tests and hopefully get the research answer. That's a reverse. You don't start with the tool. So here now we get to the tool. I wanted to tell you, right, in this case, B and C are different. How can I tell you B and C are different? I need something to measure. So what did I measure? I measure here the green here is the non-treated and red is treated. So when I use FTIR, Fourier transform spectroscopy, here you can see with the FTIR, the peaks here in the dashed line appear that did not exist in the green line. So I can tell you for sure red and green are the same. But if you look at B and C here, they are the same. So if my tool was the color, they're both cream color. That tool cannot distinguish the difference between B and C. But here, FTIR can distinguish based between A and B and C, green and red. And on the black side is even more noticeable. So this last one, black, is the carbon treated. So when you look at different peak spectra, there is a, for those of you who are not as tuned with chemistry, don't worry, there is a book that tells you what each peak means. And of course, there is a lot of literature to tell you which peak is indicator of what. I put a table here to show you which absorbance means what functional group. For instance, here is CO is appearing around 1241. Overall, what we see here is the stretching near 2850 to 3000. You can see here associated to CH stretching, and is much more prominent in treated ones. Whether it's oil treated or carbon treated, in this two is much more prominent than this green. And this could be related to the crystallinity that we change by the method that I just told you about. So they are different. And now that we made them different, the next question is, how does it help now that we change the phase? So we did another tool here. This one is Raman. So when we run FT Raman here, the ratio you can, and for all the oil treated is 1.6. That right there, it tells you the two of them are different. So two methods to show you that what you have done in terms of changing the face of plastic worked, even though the color is stayed the same. So you can see how important is now, after you know the question, to pick the right tool. But they are still just a tool. If one tool, one method did not work, like here, color did not distinguish, I go with another method. If this one doesn't work, then I go with another method. For now, we have two methods that they can distinguish. Good. The next question is, okay, now I see that surface chemistry change. I have new chemical functional group appear on the surface after I treated it. Does it mean the surface energy also change? So this is right here another tool. We use inverse gas chromatography, and with that, we measure basically surface energy. The non-treated one here had, in terms of dispersive forces, had 91 millijoule per square meter. As soon as we treated it, it became 142. So you can see the change in dispersive forces, and of course it reflects in total, which is increased. The increase of surface energy promotes interaction with surrounding material. In this case, we're gonna put plastic into bitumen. So increase of surface energy of our new plastic helps interact with its surrounding, which is bitumen. That's the hypothesis, right? If I increase the surface energy, I grafted this molecule, I'm expecting that the interaction will go up. The whole reason we wanted to make it compatible, right, to begin with, so we want the interaction be higher. So in this case, when we actually went from 91 to 142, that's a significant increase in surface energy. Now we want to know does it really interact better with its surrounding now that we change the surface? So with these three tests, we proved that what we did changed the surface, changed the plastic, even though the color did not change. So now let's see if it helps. Next, we want to see if they like asphalt. So we're going to do a separation test. We're going to dump each one of the plastic into bitumen and then measure how they separate or how much they separate. We have a test called cigar tube test, if you're familiar with. If not, it's the ASTM D7173. You can check it out. We basically put it in a tube, sort of like, we call it cigar tube, and then after conditioning, we cut the top and bottom part, throw out the middle part. And then we compare the properties of the top and bottom. Doesn't matter what properties. If this material does not change, does not phase separate, you should have same properties all the way, right? Like if you have a cup of coffee and you put some sugar in it and mix it, it should be sweet all the way. You can't say, well, the bottom is not as sweet as the top. Then you didn't do a good mixing. So in this case, when we measure the properties on the top and bottom, they should be the same. The more difference, the worse. That means they separated. So in this case, the non-treated one, which I showed you in the beginning, separated big time. That's the red line, 132% different between bottom and top. So if it was a cup of coffee, it would be like very bitter on the top, on the bottom, and maybe, or the reverse, sweet in the bottom, bitter on the top. In this case, the change was just not acceptable. These two are incompatible. You could just mix it and think you did a good job. You added all this waste plastic into asphalt, but your pavement will be terrible. It's gonna crack as soon as you place it and compact it because they don't like each other. And then in the case of the treated one, we reduced it to 18%. Still they separate, but not as bad. And in the case of the carbon treated one is 25. So we do have a threshold for the standards specification for the pass or fail. Literally all bitumen, because bitumen is not a homogeneous material to begin with. It does phase separate a bit. So there is a threshold what can be accepted and what cannot. 132 is definitely a rejection. So in this case, we improved the surface energy. As a result, they like each other better and they separated less. So far, so good. We have the separation index to tell us the improvement. And then all these other tests, they are more or less specification driven. That's why I put ASTM in case you want to do it on your side. So ASTM is a D4402 is a viscosity test. Most of you are familiar with this. When you add a new particle or granules into asphalt, what happens? Viscosity jumps up. In the case of a standard, we only look at the 135 degrees C viscosity. So viscosity at 135 for non-treated was around 2000, and then oil treated and the carbon treated were these two bars. So we did reduce the viscosity a bit, but interesting enough here, it can actually shows that when you did the carbon treatment, it was higher than just oil treated, which may even mean that the interaction with the carbon side was more because carbon literally is more compatible with bitumen, which itself is carbon based. Another method to show these materials are different is rheology or modulus. For those of you not maybe familiar with complex modulus here, G star is a measure of resistance to shear. You basically shear the samples using a parallel plate spindle at a certain frequency, and you measure how much resistance it gives to that movement. Here you can see the neat asphalt is the blue here. Neat asphalt, no plastic at all, was right here. As soon as we added each one of these plastics, it jumps up as expected. Think of you're adding something granules or powder into the bitumen, which is liquid. So it becomes stiffer and more higher modulus, more resistance to shear. And in this case, the neat was actually higher resistance right here. When we increase the compatibility, the movement was better. You can see here, the interaction was better, the movement, relative movement was better as well. But that's another test to show you that these three samples are the same. They are exact same grinding size, so particle size are exactly the same. The material is exactly coming from the same batch, same plastic, but just changing the surface properties, you can change the modulus this much. And here you can see the factors for fatigue resistant and rotting resistant. These are a standard specification. You can see for the non-treated one here, the red, G star sign delta, which is a sign of fatigue, was 60. And then you can see the numbers reduce much more, which shows improvement in fatigue. They are different, the three of them, but their improvement here it's noticeable. Interesting enough, the 34 is just asphalt. And you can see that when you add plastic, your fatigue will jump so high. So it doesn't mean by adding plastic just as is without compatibilizing them, you're doing a good thing, because the fatigue could be just lost. And now you're having a material that can be very prone to cracking, fatigue cracking. And in this case, you have rotting resistance. For the neat, it was low because it's just a bitumen, nothing in it. And when we added this material, it becomes stiffer, so it was higher. And then in case of the carbon, this green one was the highest. Again, another tool, and it shows the changes. So far, you can see that when you change the surface of something, you are actually changing its behavior. So imagine now, if you have different plastic with different surface properties, of course you will get different performance. So not all plastic are the same. Some could be compatibilized with asphalt. Like here, we showed that this specific plastic could be compatibilized. And we have a series of properties. Now it's talking about low temperature cracking. So you may have a case that you're improving rotting, fatigue, viscosity, and then it gets to low temperature cracking, you can lose it there. If it's not improving, then you can still not use it, because we have a bunch of specification thresholds for low temperature cracking. As you know, with stiffness and M value, we have to meet those as well. So for low temperature cracking, when the material is at very low temperature, sub-zero, is very stiff, that means it's prone to cracking. In this case, you can see the neat, and then when we add the compatibilized plastic, this three. Same thing with M value. So M value is the axis, the vertical axis on the right. You can see the change of M value here, which has, according to a standard specification, the stiffness have to be below 300 and M value has to be more than 0.3. So anything less than that, it will be failing. So after you even meet all those specification criteria, you have to worry about how my material will age over time. Some material, they may be very good at the beginning, but as soon as you expose them to 1 or 2 cycles of aging, they will just degrade really bad. So we have to look at the aging, and I caution you again when we talk about rejuvenation later on, when you improve a property at the unaged status, you're not done. You have to look at how is the aging trajectory of this material, because it could be really bad after several years, and you don't change the asphalt every year. You're designing for many years. So aging test is important. In this scenario, we actually did aging index, which is one based on thermal aging and one is based on UV aging. So the one on the left here is when we put the sample, each one of these asphalt sample having different plastic under intense UV aging. We aged it for 200 hours under UV. And as you can see, the aging index, it's going up. The yellow here is neat, and you can see after 200 hours compared to 0 hours, yellow one is going sharply up. If you remember, we always talk about plastic not going away, not degrading. That's why it's lasting and it's remaining in the environment. That's why it's problematic, because plastics are not easily degradable. So in this case, actually may be helping us, because if it's so durable that doesn't go away, it may be actually good for the aging resistant. And in this case, if you look at the red and green, red is actually not treated, it's just a plastic, and green is treated. You can see they're aging nearly the same, but all of them much better than the neat. So addition of the plastic, it might be because the plastic is actually working as a sacrificing agent, is helping delay the aging of the bitumen as a whole. Same thing with thermal aging. The figure on the right here, it shows you when you actually put the sample under thermal aging, not UV, not ultraviolet, which is solar, right? The one on the left is representing sort of solar degradation when the pavement is sitting out under intense summer sun. And the one on the right is showing thermal aging. So when we do a short-term, RTFO is representing short-term, PAV representing long-term aging. You can see how the aging index goes up with the blue, which is neat asphalt, is going up. And we always expect that. We always do aging. We know that it's getting worse, but we just don't want it to get worse that fast. We don't want it to get worse that much. We want to delay it. So in this case, when we added the plastic, the bars are always shorter, and the rate of increase, when you go from unaged to RTFO to PAV, if you look at how fast they increase, that's much lower than the slope or the rate that you see for the neat. So maybe plastic is delaying the aging in this case. So this was actually much more interesting to us than all the rotting and fatigue and all these other characteristics, even though we have to meet those, right? If you don't, then you can't even use it on the road. But the most interesting part to us was this aging. What does it do to delay aging so much? So we had to do a bit of molecular modeling. I'm not going to go too much in the chemistry. For those of you who are interested, I'll refer you to the paper that we published on this. But if you think about all the molecules of the oil, which we put on the face of the plastic, these are the molecules. So we basically put these molecules on the face of the plastic. And this one here on the left is the plastic. So when you get the plastic, cover its face with this oil, and then mix it with asphalt here, you will get something like this, grafted. So oil are grafted to the plastic and become like this, the one on the right. And when it becomes so grafted, when the oxygen come to attack the material, they will be delayed. So some of this aging will be delayed because of the interaction. One other element, so free radicals and aging products will be delayed. Another one is loss of compounds like benzoic acid, hexadecanoid. These are compounds that are in asphalt, and they lose and they go out as volatile as the aging happens. So if you think about the surface of asphalt as it may not be the best analogy, but the brand new asphalt is very black. And after many years, it becomes more like whitish, grayish color. If you just as a simple analogy, what happened from black to that color? And of course, then you have all the cracks and things that happen in the old asphalt. Well, one reason is oxidation, which we always look at how the oxidation happened. But another reason is some of the components in asphalt are going to air as a volatile. So they're gone, they're lost. And that contributes to aging. So if they more and more compounds of asphalt, which they are supposed to be inside asphalt, they go out and they leave the asphalt weaker. As a result, it becomes more prone to cracks and degradation. So what happened here, asphalt, that when we have this plastic, now they are keeping it in because of a good interaction between them. They don't let them evaporate or emit to air. So in summary, I want to tell you that when you actually use a new material, a recycled material, whether it's plastic like we just talked about, or any other so-called waste, you need to figure out if they are compatible. That's the very first step. And then if it's not compatible, the second question is, can it be compatibilized? Can it be compatible by doing something to it? So in this case, treatment of plastic, in case here is polyethylene tetrafluoride, PET, actually improve compatibility. And it showed that we have a Raman test to show we increase crystallinity. The surface energy was increased by 49%. In addition to that, we had significant reduction in separation, which proves that they like each other more. They're not 100%, they're not gonna, love each other, but they like each other. So that's better than none. And then hybrid treatment, when we added carbon on top, that was even better because when graphene coating happens onto the plastic, is very compatible with asphalt, which is carbon-based itself, and it improves crack resistance. And overall, introduction of this plastic, either way, even the one that is not compatibilized, the non-compatibilized one, it still improves aging. It's just not compatible, so it's gonna crack. So you have to think about what properties I want to measure and what tools I want to use. But then to use it on roads, you have to meet all those properties, because you don't want to improve one and then fall into another trap, another hole. So in this case, all the plastic we use, regardless of treatment, they improved aging significantly, both under UV and much more durable. So with that, I want to leave some time for question. Let me stop and see if anyone has question. I guess you were supposed to send questions to Ali.
Okay. Okay, thank you so much. Thank you so much, Dr. Fini, for very excellent presentation and a really very informative presentation, and we learned many new things. And thank you so much about using plastics, and just not to use plastic, but use the right plastic material and add them to the asphalt as a modifier, and or making more, making more sustainable material. And of course, we help to, asphalt material be more, resistant to different, circumstances during the service of the pavement, asphalt pavement, and etc. So it's quite very interesting topic, and very, very, the things around this area is now developing. And thank you so much for this presentation, and I hope all attendees are enjoy and by listening and seeing this these findings and these results. Thank you so much. Yeah, I got several questions till now. Yeah, 3 questions from thermoreversible aging or physical hardening of modified asphalt. One question was about that. Yeah.
That's an excellent question. Whoever asked that, this is actually the ongoing study, this physical hardening. And if you're interested to pick that as your thesis or dissertation, this has a lot of room to work with. Even with this plastic, we haven't completely addressed the physical hardening. And much like when you have a lot of wax in asphalt, which you get physical hardening, you will get physical hardening with plastic as well. And addressing that, whether you're going to use a compatibilizer or somehow prevent that, is critical. You will see that somehow in the thermal cracking results, but still that's not as well measured. So one research we are doing, we are looking at continuous extended conditioning, not a typical BBR for sort of thing. You extend the conditioning and you see that the hardness, the stiffness of material builds up. So if you're interested to look at that, we have not, and I don't have an answer yet. Good question.
Okay, great. Thank you. Thank you so much. Yeah. And yeah, next question is about, does the method of adding waste oil to the plastic granules open up opportunities to use plastics from the other categories, or the ones that are not so easily recycled?
A smart question. That's great. So some of this plastic, as I showed you, they're not even recyclable. So if we can grind them, but all of them are grindable. So let's put it that way, like PVC, all of them can be grinded. One problem with most of this plastic you have to watch for is if you can create microplastic and cause contamination and leach it afterward. Otherwise, you can compatibilize most of them. We have not dealt with every one of them. We have dealt with HDPE and PET and PE. So if you are interested to look at other plastic, that's definitely a good topic. It's starting, it's hot topic now, and there's room to do things. But as for the overall concept of oil treatment, this specific oil grafted well on PET. I don't know if this same oil will graft well on PVC or on HDPE. So you have to find the right molecules that graft onto the plastic that is your choice. Of course, you are welcome to start with our process, with the waste vegetable oil grafting, and see if you get results. If not, there is always molecules that improve interactions. Think of it like a magnet. If I have a piece of plastic and I cover like a ping pong, a ping pong, and I cover that by magnet, now I can attach it to the fridge or to the metal. Before, it wouldn't, right? Ping pong would not attach to the fridge. But when you coat it with magnet layer, it does. Similar concept applies here when you change the surface properties. But not every bio oil will treat every plastic. You have to tailor your design for that specific plastic.
Okay, yeah, thank you. Thank you so much for the full response. Yeah, the next question is mentioned that in the experiments, waste plastic has been added as a raw material, but has the amount of traditional raw materials been reduced as well? Does that make sense?
So in case of asphalt, this is a good question, but in the case of asphalt, there is different because we are not adding any polymer now. We are using this plastic sort of, as to improve the stiffness and cracking and this. So the answer is yes, if you would have add other material or if you would have add rubber. Remember, those of you who are familiar with rubberized asphalt, we add like 10-15% of rubber granules. In this case, we are adding plastic. So if a good comparison could be and we are publishing a paper in this soon in, I think, in construction building material that is talking about, can we use granules of plastic instead of granules of rubber? Can we get similar performance?
Okay, great. Yeah. And the last question that I got till now was whether the molecular model established was a two-layer model or not.
So in the molecular model, we started with the plastic molecules itself, we build one for PET, and then we build and optimize a separate one for the oil. So the interaction of the oil and PET become a third model. So if you're referring to as a two-layer model, each one of these optimized separately, and then the model of plastic oil was built. When you have then the grafted oil, which we call it OTPG, when we have oil-treated plastic granule model, which is basically oil-covered plastic, then this model was interacted with asphalt. So when I told you that benzoic acid, for instance, had a very good adhesion bonding to plastic, was the oil-treated plastic. It doesn't have good interaction with other plastic. It has, with the treated one, we measured the bonding.
Okay, great, thank you. And yeah, another question I received now is asking PET fiber, which used to enhance the performance of asphalt mixture, or PET modified asphalt to strengthen the binder. Which one is better?
Yeah, that's a very good question. As I don't have an answer to that because we only worked with PET that is added to binder. I think the fiber has reinforcement effect. In the case of PET added to binder, it's more as a binder extender. So different role.
Okay, great, yeah. And yeah, I got another question now. Yeah, very good. What is the effect of irradiation in the preparation of oil-treated plastic granule?
If you're referring to the method of making the granules, the coated granules, you need to graft the molecules of bio-oil somehow to the surface. If you just pour it on it or soak it, is not enough for grafting. You need to be able to attach the molecule. So we use a mild radiation to ensure grafting, and then we wash it with acetone. So this is not a simply like mixing plastic with oil and that's it. Because if you just mix it, it will be washed away. It's not attached. So after the radiation, it's attached and we wash the excess material with acetone. So the coated granules are literally washed. Surface.
Okay, yeah, great. Thank you everyone for attending this presentation and the question, which means that really our attendees are very interested in this topic. Thank you everyone for your active participation. And yeah, I would like also to mention that this session is recording, so we will later share this the link to all attendees. We will share in our website. And also no need to mention that, as Dr. Fini mentioned, our next lecture presentation will be on 24th December at 10 a.m. Beijing time, with the title of "Do Regenerators Revitalize Aged Asphalt?" So I think it is also very interesting topic and title in this area, and we are looking forward to hearing Dr. Fini next presentation. And thank you so much, Dr. Fini, for taking the time to present this very interesting contents about your research. We really learn many things about it. Thank you so much. Yeah, thank you, and thank you everybody for attending this seminar and this press lecture series, and we are looking forward to meeting you all again.
Thank you, Ali.
Thank you. Thank you, and see you everybody. See you all. Thank you. Bye-bye. Have a good day there. Yeah.
Thank you.